Hanukkah candle, the Hanukkah candlestick that I was talking about. This week, I think, this year, sorry, it's December the 22nd, last year it was December the 21st, the year before it was December the 20th. It hovers around this date of the winter solstice. You can position the same design of the candlestick pointing out in any direction that you wish. You're dividing the year into 16. That's 8 divisions of the year. 8 divisions from June to December. Using this device here, geometric device here. You put this whole thing back into the picture again. There's the Earth again, there's the Sun, here's our theoretical 8-sided here. You put this in here and you can start looking at which are the best circumferences of circles to determine how degrees relate to days. We're talking here about the solution, how degrees relate to days. The actual degrees that we're using was something like 5,184 instead of 360. And you get that simply by multiplying 360 by 1.44. It gives you 518.4. 518.4 is in exact ratio to 25,920 years, which is
precession cycle.
The precession cycle, so you can also use this to measure precession. And look at this one here, you've got 4 clocks. You can put one in the center as well. You've got 4 clocks in the center, stick one on the outside. What is that starting to look like? A Celtic cross, we might say. The pentagon here is based on 5 moons distance. So this array of days here is actually on 6. So on the area of influence of 6 moons. So 6 moons it is from the center, 6 moons from the center, and this circle here is in relation to 5 in relation to this 6 and this 6. So this is 12 and this is 5. And when you get something like 12 by 5, then again all astroarchaeologists ears prick up, because 12 by 5 is one of the major rectangles, types of rectangle that you find in megalithic sites, especially on the old favourite Stonehenge. So once I've found that these things relate to degree days, and we've got a circle of the Earth here, also I suddenly realised, maybe there's something to do with 12 by 5 rectangles here. Now this is the work of Robin Heath. You draw any 12 by 5 rectangle, and you call this top of it 12, and you call this one 5, and then you draw a line up so that this becomes 3 units. And this 3 units here and this 12 units give you a hypotenuse. The square on the hippocampus is equal to, you know this one. 12 times 12 is 144. 3 times 3 is 9. So you get the square of 153. The square of 153 is 12.369. 12.369. 12.369 just happens to be the number of moon months in one solar year. This is research already established by, I think it was Robin Heath or Newman or one of these researchers. That distance there, from there to there, on any of these rectangles, can determine the number of moons in one solar year. I've got a clock here that changes according to how large you make this, and as the clock changes, this rectangle, the rectangle that I've got here, I took the other clock out to make it more simple to understand, but these 2 clocks here are changing inside depending on how big a circumference you want these circles to be. As they change in size, these, like a pair of scissors, are changing as well. And as they change, they hit the Earth's surface and then move gradually and slowly up into the upper atmosphere above your heads. There's the first one. Nobody saw this one before. This is your first. This is the first time I've talked about this one. There is an Earth circle in the center of a 12 by 5 rectangle, determined geometrically, and if that is going to be accepted as fact, then there's an Earth circle somewhere on Stonehenge. Because the most famous 12 by 5 rectangle that we know of is the one on Stonehenge called the Station Stone rectangle.
There's also the 12, 13, 5.
12, 13, 5?
Yeah, from Heath. The ratio 12, 13, 5 making that.
Okay.
And if you go from Edinburgh to London to Cardiff, that triangle is the ratio about 12, 13, 5.
Yeah, and the 13 is the diagonal.
Exactly.
Yeah. This distance from here to here is 13.
That's right.
Yeah. I was in Stantonbury Crop Circle. That's it there. The other last year, wandering around in the mud, trying to find it on Stantonbury Hill. I had a look at it and I thought, I know that. And I suddenly realised there's that little gap between the top of the Earth's atmosphere and the Earth's surface. I overlaid it onto my diagram, and suddenly you start to see, look, there are 12 moons around this. This is the size of the Earth. Here you've got a larger, where the edge of the crop is defined, you've got the air of the atmosphere, and these two here don't relate to the size of the moon. Well, I had a look at it. What they do relate to, if you're looking at an eclipse and the sun is behind the Earth and you're sitting on the end of the shadow of the eclipse, where the shadow of the Earth comes like an ice cream cone through space, then that would be the size of the moon that you're looking back at. Pretty amazing. I also measured this distance here. It's exactly 6 moons across. That's 12 diagonals, and these trigrams, 12 of these trigrams as well.
Colin, thank you so much for that. It's a brilliant talk. Really, really inspiring talk. I felt really guilty having to try and chase you up at the end because we ran out of time. The man sometimes gets a bit angry if you don't like it run over. But that was a brilliant talk, and I really, I was really impressed by that. There was a lot of information, and that's what I like when you get that kind of information flow happening, and things are going in, and things are starting to tweak. Brilliant, really good. And thank you for coming to share that with us, because that was really something else. So thank you again.